The universe invites big dreams, like building a ship that rides a beam of light. But the closer you chase that glare, the stranger the rules become. Einstein's special relativity says light speed isn't just fast, it's the speed limit written into space-time. Push harder, and your kinetic mass seems to swell. Clocks on your ship tick slower, and the energy bill climbs toward infinity. Try to leap past light, and quantum limits wobble while cause and effect risk flipping inside out. In this episode, we'll slow things down, keep the math light, and follow the physics to see why C is a boundary that protects reality's logic. If this gentle tour helps, a quick like and subscribe lets more curious minds join us. Settle in, let's explore the fastest speed we can never reach. About 300,000 kilometers per second, around 186,000 miles per second, is the cosmic speed limit. It shapes how atoms behave and how galaxies move. Try to catch it, and the rules of nature push back in a way that doesn't match everyday experience. The barrier is not a wall you can break with a stronger engine. It is built into how space and time themselves work. The closer you get, the more the universe demands from you, until the demand becomes impossible to meet. The path to this idea runs through Albert Einstein's special relativity, published in 1905. Before that, many scientists pictured space and time as separate backdrops, a fixed stage where events played out. Einstein showed that space and time form one connected fabric spacetime, with simple but strict rules. One rule sits at the center. Every observer, no matter how they move, measures the same speed of light in empty space. This fixed value anchors cause and effect and keeps the laws of physics consistent for everyone. Picture a ship trying to go faster and faster. As its speed rises, a subtle effect grows stronger. It gains resistance to being pushed. In older language, people called this relativistic mass increasing. In modern terms, the ship's rest mass doesn't change, but its energy and momentum do, and that extra energy behaves as if the ship were getting heavier to push. At about 1/10 light speed, this change is tiny. Near half light speed, the resistance rises by roughly 1/6. Push to 9/10, and the factor more than doubles. Climb closer, 0, 99, C, 0, 999, C, and the required energy shoots upward so sharply that reaching exactly light speed would take an infinite amount. Infinity is not engineering difficulty, it is a hard stop. This rising resistance comes with two quiet companions that keep the story balanced. Time on the fast ship runs more slowly compared to clocks left behind, a gentle effect at first that becomes dramatic as speed climbs. Distances along the ship's direction also contract from the ship's point of view, which helps keep cause and effect in order. These are not tricks of perception. They are how space-time keeps the speed of light the same for everyone and prevents signals from outrunning causality. In everyday life, you never notice this, because cars and planes move far too slowly for the effects to show. None of this lives only on a chalkboard. We see it in machines that sling tiny particles to near light speeds. At the Large Hadron Collider near Geneva, protons loop around a ring of magnets and radio cavities until they reach a speed so close to light that you would need many nines to write it. Their energies make them behave as if they were thousands of times heavier to push than when at rest. About 7,000 is a typical figure at the highest settings. Engineers can still add speed, but each extra step costs much more power than the last, like trying to push a sled that grows heavier every time you nudge it forward. That is why the barrier holds. The speed of light is not just a fast number, it is a built-in limit that keeps physics consistent. As you approach it, inertia swells, time dilates, and distances contract in just the right way to protect cause and effect. The energy you would need does not merely exceed our tools, it diverges without bound. In a universe governed by space-time's rules, almost light speed is possible, and we do it with particles every day. But light speed for anything with mass is a destination that space-time itself will not allow. Space-time enforces the limit gently but firmly, first on your inertia, then on your clock. Mass increase is only the first surprise. Time begins to slip. The effect is called time dilation. When you move very fast, your own clock ticks more slowly than a clock at rest. Clock here can be anything that measures change your heartbeat, a watch, a radioactive sample. The rule is simple to state and hard to feel, because at everyday speeds the difference is tiny. As your speed rises toward light speed, the difference stops being tiny. Minutes for you can become hours for someone watching from far away. This is not a poetic idea. It is built into space-time, so that the speed of light stays the same for everyone. We test this with machines and with space hardware, not just with theory. Satellites that guide your phone GPS are a quiet proof. The clocks on those satellites do not match clocks on the ground. Two relativity effects pull in opposite directions. Because the satellites are moving, special relativity slows their onboard clocks. Because they are higher in Earth's weaker gravity, general relativity makes their clocks run faster. The second effect wins, so the net rate is a bit faster than on Earth. Engineers program a correction before launch and keep adjusting in orbit. If they ignored relativity, positions would drift by roughly 10 kilometers per day, and maps would become useless. Near light speed, time dilation becomes strong enough to reshape trips between stars. Picture a ship cruising to Proxima Centauri, our nearest star, a little more than 4 light-years away. From Earth's point of view, a ship at 99.9% of light speed would arrive a bit over 4 years later. Inside the ship, the crew would feel far less time. Their onboard clocks would measure only a few weeks, about 2 months, because their time is slowed relative to Earth. Push closer to the limit, adding more nines to that percentage, and the ship's travel time shrinks further for those on board, falling to days. The distance is the same for Earth, but not for the travelers. Space-time allows both to be true. This leads to the famous twin paradox. Imagine one twin stays on Earth, while the other rides a near light speed loop to a star 25 light-years away and comes home. The Earth-bound twin would see about 50 years tick by. The traveling twin would age far less, depending on the speed profile and the accelerations for turning around. There is no real paradox once you recognize that the traveler changes frames by speeding up, turning, and slowing down, while the twin at home does not. Space agencies have tested pieces of this with fast particles and with precise clocks on aircraft and satellites. The results line up with relativity every time. Energy demands bring another wall into view. As speed rises, the energy you must add to keep increasing that speed grows steeply. In modern language, we say the object's rest mass stays the same, but its energy and momentum rise according to a factor called gamma, which explodes as you approach light speed. That energy is not just a number on a whiteboard. It is the work an engine must do and the heat a system must manage. Even for a 1 kilogram payload, getting to a large fraction of light speed would require energy on the scale of national power grids. Each extra 9 in your target speed multiplies the energy cost by several times more. Reaching exactly light speed would require infinite energy, which nature does not hand out. Our best spacecraft show how far we have yet to go. The Parker Solar Probe, diving deep toward the Sun, has reached about 195 kilometers per second. That is blistering by human standards. At that pace, you could race around Earth's equator in only a few minutes. But compared to light's 300,000 kilometers per second, Parker is at roughly 0.065% of light speed. Even after decades of rocket progress, we are not close to 1%. Voyager 1, the farthest human object, coasts at about 17 kilometers per second after more than 40 years. At that rate, covering a single light year would take on the order of 17,000 years. The gap is not just wide, it is vast across many kinds of engineering. Relativity also reshapes space itself along your direction of travel. The effect is called length contraction. From your seat on a near light-speed ship, distances ahead shrink. That 4+ light-year hop to Proxima would appear much shorter at 99.9% of light speed, on the order of a few dozen light days, roughly 2 months of light travel. This is why the crew's own travel time can be so small while Earth still measures years. Time dilation and length contraction are two sides of the same rule set that keeps the speed of light fixed. Pushing the idea to its limit teaches a careful lesson. Along the path a photon takes, the proper time experienced by the photon is 0. In loose language, people say, no time passes for light. Strictly speaking, light has no rest, framed the way matter does, so we avoid talking about what light feels. The safer statement is that, as your speed approaches light speed, the proper time along your path between two events tends towards 0. This is the edge you cannot cross if you have mass. You would need to live on a timeline of 0 duration, which massive objects cannot do. All of this ties back to Einstein's simple relation between energy and mass. E equals mc squared. Mass is a form of energy. Energy has mass-like effects. When you pour energy into an object to make it go faster, that energy adds to the total you must push. It is as if each burst you add makes the object harder to budge next time. The bucket you are trying to fill grows heavier with each drop, and the ladder you stand on grows taller. The curve does not level off. It gets steeper without end. The speed of light itself was not easy to pin down. People once argued whether it was infinite. In the 1,670 seconds, Ole Rømer noticed that the eclipses of Jupiter's moon Io showed small timing shifts depending on Earth's position in its orbit. He reasoned that light needs time to cross extra distance, so its speed must be finite. In the 1,840 seconds, Hippolyte Fizeau used a spinning toothed wheel and a distant mirror to time how long light took to travel down a long path and back. Later, Albert Michelson refined such methods with rotating mirrors and produced famous high-precision results. Today, lasers and atomic clocks push the precision so far that we fix the meter by defining the speed of light as an exact number. The constant is not just measured, it is woven into our units. Your view of the sky would also change as you accelerate. Relativistic aberration would gather the stars into a bright, shrinking circle ahead. The rest of the heavens would fade toward the edges, and behind you would dim to near darkness. At the same time, the headlight effect and Doppler shift would push the colors around. Light in front of you would slide to shorter wavelengths, blue, then ultraviolet, then X-rays and gamma rays as you add more speed. Light behind you would stretch to red and then to wavelengths too long for your eyes. The scene becomes harsh and narrow. At very high speeds, the forward glow would shift into dangerous radiation that can penetrate materials and damage living tissue. Electromagnetism itself looks different at high speed. Electric and magnetic fields are two faces of one thing. and they transform into each other when you change frames. In the lab frame, a fast-charged particle carries fields that are compressed and strengthened in the transverse direction by the same gamma factor that appears in time dilation. As gamma climbs, bending the particle's path takes stronger magnetic fields or a much larger ring. That is why accelerators use powerful superconducting magnets and still need vast tunnels. The effect is not merely a design headache. It is a sign that nature is warning us about the cost of chasing the limit. Holding matter together becomes harder in this environment. Fast charged particles radiate when you bend their paths, dumping energy as synchrotron light. Electronics bathed in intense blue-shifted radiation will glitch or fail. Materials struck by high-energy particles heat, crack, and spore. Polar molecules can realign. Chemical bonds can break. Biology copes poorly with ionizing radiation that tears through DNA and proteins. Even before you get near light speed, these stresses pile up. The ship must shield its crew and systems, but heavy shielding adds mass, which then needs even more energy to move. You cannot insulate your way out of the basic trade-offs. Space between the stars is not empty, either. It holds a thin gas of hydrogen and helium, small dust grains, and a rain of cosmic rays. At normal speeds, a few impacts per second are harmless. At relativistic speeds, each hydrogen atom slams into your hull with the energy of a small particle accelerator event. A grain of dust hits like an explosive. The faster you go, the more severe the battering, and the more secondary radiation you create inside your own shielding. Estimates show that at speeds with many nines, the radiation dose from plowing through interstellar gas would be comparable to lethal exposures near unshielded reactors. The armor thick enough to survive would be so heavy that you could not reasonably accelerate it, circling back to the energy wall again. People ask about clever workarounds. Could you bend space-time instead of fighting it? Ideas like wormholes and warp bubbles live inside general relativity's equations. A wormhole is a shortcut connecting distant points. A warp drive would contract space in front of a ship and expand space behind it, carrying the ship inside a bubble while locally staying below light speed. The math allows such shapes, but they seem to require exotic matter with negative energy density to hold them open or to shape the bubble. We do not know if such matter exists in usable amounts. Early estimates for a warp bubble's energy were absurdly huge planet-scale mass energy. Newer versions have lowered the numbers, but still sit far beyond any technology we can foresee. Even if the energy budget was solved, building and steering such structures would pose deep stability and safety questions. Quantum physics offers no free pass. Entangled particles show instant correlations, no matter how far apart they are, which tempts people to imagine faster-than-light messages. But the correlations are random until the results are compared with a regular, light-speed signal. You cannot control the outcome of a quantum measurement to encode a message. Nature keeps causality safe. This no signaling rule is as solid a guardrail as the speed limit itself. Causality is the quiet reason for all these barriers. If signals or ships could outrun light, different observers could disagree about which event caused which outcome. In some frames, the effect would come before the cause. With the right arrangement, faster-than-light travel lets you draw loops in space-time that bring information back before it left, the seed of time travel paradoxes. Relativity's limit keeps such loops from forming in ordinary physics. It does not stop us from traveling fast. It stops us from breaking logic. What remains is still rich. Almost light speed is not a slogan. It is a real range where particles, and perhaps tiny probes, might go. time dilation can be a tool for science. Length contraction helps explain how these effects fit together without contradiction. The electromagnetic field's behavior at high speed teaches us how accelerators must be built. The interstellar medium's hazards tell us what any practical starflight design must face: shielding, clever routes, perhaps magnetic or plasma shields to deflect charged particles, and strict limits on peak speed. The goal is not to bulldoze the laws of nature, but to learn how to work within them. In that light, the reason we cannot reach or exceed light speed is not a failure of engines, materials, or ambition. It is because space-time sets the rules that make a coherent universe possible. As you push toward the limit, time slows, distances contract, fields intensify, radiation hardens, and energy costs climb without bound. Every path to the barrier confirms the same message. The speed of light is not just a number, it is the structure that holds cause and effect together. You can see these rules reach into matter itself. At high speed, even an atomic nucleus changes shape. At very high speed, even the shape of matter changes. At CERN, when heavy atomic nuclei are pushed close to light speed and smashed together, they do not look like quiet spheres anymore. Because of length contraction, the rule that distances shrink along the direction of motion, a gold nucleus flattens into a thin pancake. The thickness can drop to less than a femtometer, which is smaller than the size of a single proton. This is not guesswork. The flattened shape shows up in the spray of particles that flies out after the collision. The splash pattern carries the footprint of the original geometry, letting physicists read the shape the way you read ripples to learn about the stone that made them. Cosmic scale brings a different kind of limit. Galaxies far enough away can recede from us faster than light, and relativity is not broken when that happens. The galaxies are not racing through space like a rocket. Instead, the space between us and them is stretching. Because of this, there are regions we will never reach, no matter how long we try or how advanced we become. There is also a horizon for light itself. Some places will never send us a signal that can arrive, because the expansion carries them away too quickly. The part of the universe we can observe is bounded by this race between light trying to cross the distance and space making the distance larger. Quantum rules add their own stop signs. The uncertainty principle says we cannot know a particle's exact position and exact momentum at the same time. As speed rises and relativistic momentum grows without bound, trying to lock down both numbers fails. If you squeeze the spread in momentum to control the motion, the spread in position grows. If you hold position tight, the momentum becomes poorly known. In plain terms, the wave packet that describes the particle will either blur out in space or in speed. For everyday objects, the blurring is too small to notice. Near light speed, this basic trade-off tells us that perfect control of a massive object's path is not available, no matter how clever the pilot or the machine. Living systems run into limits before the physics does. Human bodies evolved for gentle gravity, modest speeds, and a calm radiation background. When you try to reach a large fraction of light speed, the hard parts are not just engines and fuel. Getting there requires long periods of strong acceleration, and strong acceleration pushes blood, strains tissues, and stresses the nervous system. Even if a craft could ramp up slowly to spare the crew, the environment ahead becomes harsh. Interstellar gas and dust turn into high-energy projectiles in your frame. Blue shifted light hardens into ultraviolet, X-rays, and gamma rays. Electronics suffer upsets, DNA collects damage, repair systems fall behind. In your own coasting frame, chemistry still follows the same local rules, but the bath of radiation and particle impacts grows severe enough to overwhelm biology. The mind faces its own burden. Time dilation stretches the gap between your journey and everyone else's. Months for you can mean decades on Earth. Coming home would feel like stepping out of a quiet room into a city rebuilt twice over. Friends aged, customs changed, language shifted. None of that breaks physics. It is simply what the equations predict for clocks that took different paths through spacetime. The psychological cost is hard to model, but easy to imagine. Energy density brings a deeper warning. Energy and mass are two expressions of the same thing. When you pour enormous energy into a small volume, gravity takes notice. In principle, concentrate enough energy in a compact region and you can form a horizon, a black hole. This idea is captured in thought experiments like the Hoop conjecture. Real starships would be nowhere near such extremes, but the lesson stands. The energy bill does not just rise, it piles up in a way that can curve spacetime itself. The limit is not only hard to pay, it changes the shape of the game board. Even the vacuum is not simple at these extremes. Quantum field theory treats empty space as a restless sea of brief particle pairs that pop in and out. Under steady coasting, you do not feel this activity. Under extreme acceleration, a new effect appears. An accelerating observer perceives a warm background, a kind of heat bath called the Unruh effect. The temperature grows with acceleration, not with speed, but the accelerations needed to push a crewed craft quickly toward relativistic flight could, in principle, make this bath intense. That adds another source of radiation stress to any design that tries to get fast in a hurry. Light itself points a narrow beam as speed grows. Relativistic beaming squeezes any radiation you emit into a tight cone pointed forward. Headlights would become a piercing lance of energy. Little would spill to the sides. The same narrowing affects signals. Radio and laser links would be driven into narrow beams with strong Doppler shifts. Receivers behind you would struggle to see the engine glow. Receivers ahead would see frighteningly energetic flashes. Communicating with home, while moving at such speeds, would demand precise pointing, careful frequency planning, and hardened gear. The universe ahead would look like a bright circle of compressed starlight. The sky behind would fade. Our fastest probe makes the gap vivid. The Parker Solar Probe dives close to the Sun and reaches around 200 kilometers per second. To human senses, that is astonishing. You could circle Earth in minutes at that pace, yet it is only a small fraction of 1% of light speed. Reaching even 1% would require far more energy and a different kind of propulsion. Gravity assists, careful navigation, and tough heat shields can buy speed near a star, but they do not bend the basic limit. Nature itself runs particle tests for us. Cosmic rays, protons, and nuclei whipped up by supernovas, black hole jets, and other violent engines arrive at Earth with energies beyond what our biggest machines can supply. One famous event, nicknamed the "Oh my God" particle, carried in a single proton, an energy like a thrown baseball. Even so, its speed was still shy of light speed. The difference from c was tiny in fractional terms, but not zero. Relativity left no loophole even at that scale. Orbiting clocks keep the daily books. GPS satellites move only a few kilometers per second, but their clocks tick at a slightly different rate than clocks on the ground. The combined effect of speed and weaker gravity adds up to tens of microseconds per day. Engineers correct for this all the time. If they did not, navigation errors would stack up to miles within days. If such small speeds already need relativistic care, you can sense what happens when the target is a speed that pulls the factor gamma into double digits, then triple digits, and beyond. There is a final picture that helps explain why the limit cannot be crossed by matter. As speed approaches the speed of light, length contraction in the direction of travel grows stronger and stronger. In the strict limit at light speed, the contraction would be total, and the proper time between emission and absorption would be zero. We avoid saying, from a photon's point of view, because light does not have a rest frame the way matter does. The careful statement is that for null paths, the paths light follows, the interval of spacetime is zero. A massive object cannot ride a path like that. To do so, it would have to give up having any proper time at all. That is the cliff's edge, and it is not one we can step over. Taken together, the signs point the same way. High-speed nuclei flatten and tell their story in the debris. The expanding universe hides regions beyond reach without breaking the rules. Quantum uncertainty resists perfect control as momentum soars. Bodies and minds built for Earth struggle under acceleration, radiation, and long separations in time. Energy piles up, space itself can curve, and even empty space grows noisy under extreme acceleration. Beaming narrows light and radio into hard spheres. Probes and cosmic rays show how close you can get and how the last little bit never arrives. The speed of light is a boundary, not because our tools are crude, but because the structure of space-time keeps cause, effect, and information in a workable order. You can even watch this boundary surface when light slows inside matter, written in the soft blue of Cherenkov radiation. Light keeps a special status even when it seems to give ground. In water or glass, light moves slower than in empty space. Charged particles passing through can outrun light's speed in that material and leave a soft blue glow called Cherenkov radiation. It is the optical version of a sonic boom, a wavefront that forms because the particle's disturbance propagates faster than light can catch up inside the medium. The key rule remains untouched. Nothing with mass beats light's vacuum speed. The blue shimmer in a reactor pool is proof of the limit, not a loophole around it. Another test arrives from the fabric of space-time itself. Gravitational waves are ripples in space-time made by violent motions like colliding neutron stars. When LIGO and Virgo saw such a merger about 130 million light-years away, telescopes also caught the light from the same event. Both signals crossed the cosmic distance and reached Earth within seconds of one another. That near tie confirms that the ripples and the light share the same speed limit. The result goes beyond electromagnetism. It ties the limit to causality, the rule that causes come before effects, and to how all information crosses the universe. People have long wondered whether there might be particles that always move faster than light. These hypothetical travelers are called tachyons. If they existed, their mass would appear imaginary in the math. They could never slow down to light speed, and in some frames they would run time backward, inviting paradox. Careful searches in many kinds of experiments have found no sign of them. The simplest reading is that nature does not allow that route. Keeping everything below light speed keeps logic intact. In some advanced models of physics, the limit looks even more basic than a speed cap. String theory and other ideas that try to join quantum mechanics with gravity often treat the speed of light as an emergent property of the deeper geometry. In that view, c is not a dial we can turn, but the maximum rate at which information can be braided through the extra structure of space-time. Whether those models are correct or not, they point to the same everyday rule we measure. Nothing carries a message faster. Even if physics allowed a bigger number, the energy bill would stop us. Pushing a small craft toward a large fraction of light speed demands staggering energy. Estimates for a 1-ton probe reaching 90% of light speed land around many years of global energy production, and that assumes perfect engines with no losses, which do not exist. Real systems waste heat, spill radiation, and must carry equipment, fuel tanks, and shielding. The practical tally climbs even higher. The rocket equation deepens the trap. Each kilogram of propellant you load is cargo you have to accelerate, which means you need more propellant, which makes more cargo, and so on. The growth is exponential. Chemical propellants, which store energy in molecular bonds, run out of room fast. Reaching even 1% of light speed would ask for impossible fuel masses. Nuclear options do better, but still fall short once you include tanks, radiators, and structure. Antimatter looks perfect on paper because it converts mass to energy very efficiently, yet we only make it atom by atom in labs, and storing macroscopic amounts safely is a problem we do not know how to solve. Even if production and storage were solved, the amounts required would still be measured in tons for serious speeds. The universe itself adds distance you cannot buy back with speed. Space is expanding, and the expansion is accelerating because of something we call dark energy. Far-off galaxies are carried away by this stretching. Beyond a certain range, their recession exceeds light speed. That does not break relativity, because the galaxies are not moving through space faster than light. Space itself is widening. The result is a horizon. There are regions whose light will never reach us, and regions we can never reach, even in principle. At the level of atoms, motion at high speed changes how outside forces look, but it does not make local physics fail. In your own coasting frame, chemistry still works by the same rules. The trouble is the environment you would face. Fields transform, radiation hardens, and impacts with interstellar gas strip electrons from atoms. Ionization, heating, and mechanical damage overwhelm fragile structures long before any relativistic chemistry would matter. Heavy element chemistry in everyday life already shows small relativistic tweaks like gold's color and mercury's liquidity, but those come from electrons near the speed of light inside atoms, not from your ship's bulk motion. Near-light flight simply bathes everything in conditions that erase the delicate electron arrangements life depends on. Vision and perception do not survive unaltered either. The Penrose-Terrell effect tells us that a fast object does not merely look shorter, because light from different paths takes different times to reach your eye. The object appears rotated. A moving cube can seem to show a face that ought to be hidden. Pair that with aberration and Doppler shift, and the star field becomes a tight, bright circle ahead. The rest of the sky slides away. Colors in front of you shift to blue and beyond, into ultraviolet and X-rays. Behind you, they stretch to red and then to wavelengths your eyes cannot see. Navigation by familiar constellations would fail. Instruments would have to point within narrow cones and correct constantly for frequency shifts just to keep lock on a beacon. Thermodynamics stays in charge through all of this. There are no real paradoxes where heat runs backward or the arrow of time gets confused. But the practical problems are severe. Waste heat has to go somewhere. At high speed, radiators must dump energy into a forward blaze sky that reflects it back as blue-shifted radiation. Accelerating hard adds the Unruh effect to the mix, a faint thermal bath associated with acceleration. For ordinary spacecraft, it is tiny, but it reminds us that pushing faster is never free. Heat management always sits beside propulsion as a gatekeeper. Too little radiator and systems cook. Too much radiator and mass kills your delta V. The same speed limit shows up in other corners of physics. In transparent materials, the blue glow of Cherenkov radiation flags, particles outrunning light's reduced speed in that medium, while still obeying the vacuum limit. Across the universe, the near tie between gravitational waves and light from the same event shows that the limit belongs to spacetime, not just to electricity and magnetism, Workarounds like tachyons remain absent from experiments, and theories that try to go deeper usually build the limit into their bones. On the engineering side, energy demands and the rocket equation close the door. On the cosmic side, expansion moves the target faster than we can chase. On the local side, atoms, instruments, and living cells fail under radiation and impacts. Step by step, different lines of evidence point to the same boundary. Yet these limits do not make the world smaller. They make it coherent. They explain why signals arrive in order, why experiments give the same result for different observers, and why navigation and communication can be planned at all. The speed of light is not just a fast number on a chart. It is the pace at which information threads through space and time, the tempo that keeps cause and effect in tune, and the frame that turns the vast, bright universe into a place we can measure, map, and understand. Within that same frame, the rule becomes hands-on in the lab. Curve a fast-charged particle, and it answers with light. This loss is called synchrotron radiation. In a straight line, the leak is small, but bend the path with magnets, as every circular accelerator must, and the particle sprays energy away as radio waves, visible light, and X-rays. Push closer to light speed, and the loss climbs sharply. In machines that fling light electrons, the drain is so strong that extra power mostly becomes radiation, not speed. This is one reason big colliders use heavier particles like protons and build very large rings. A gentler curve wastes less energy. The picture is simple to hold in mind. You pour energy into the bucket. The faster you go, the bigger the hole gets. Mass itself likely ties into a deeper field. The Higgs field fills space the way air fills a room, and particles gain mass by interacting with it. At everyday speeds, that interaction looks fixed. Near light speed, we do not expect the Higgs to switch off, but we also do not know every detail of how extreme motion and high fields might couple. Some ideas suggest the Higgs could be part of the reason the limit is absolute, not just difficult. This is an active area of theory, and the safe statement is modest. Nothing we know about the Higgs opens a door past the speed of light. Hard numbers from serious design studies show the scale of the challenge. In the 1,960 seconds, Project Orion sketched a ship pushed by repeated nuclear blasts, a kind of flying shock absorber riding a series of controlled explosions. Even with thousands of devices and bold engineering, the top cruise was only a few % of light speed, roughly 3 to 5. In the 1,970 seconds, Project Daedalus proposed a staged fusion rocket fueled by helium-3, burning for years. On paper, it could touch about 12% of light speed after decades of acceleration. Both concepts were daring. Neither came close to the limit, and both demanded technologies we still do not have in full. The space between stars is thin, but not empty. At 10% of light speed, a speck of dust strikes with explosive force. At half light speed, the same speck is a disaster. Near 90%, even lone hydrogen atoms hit like tiny bullets from a particle gun. Each impact showers the ship with secondary radiation. Shields that could survive would be thick and heavy. Their mass would push fuel needs through the roof. The faster you try to go, the more space itself fights back. Quantum behavior does not simplify the task. Particles can sometimes tunnel through barriers they should not cross in classical terms. Changing the energy and momentum ranges can change the chance of tunneling. At extreme speeds, those probabilities may shift in ways that affect nuclear reactions or bond breaking. We do not have a complete map for such regimes, But nothing in tunneling offers control over faster-than-light motion or a reliable shortcut past the engineering limits. If anything, it adds another layer of effects a real vehicle would have to manage. Communication runs into its own wall. A ship moving at 99% of light speed would see light from home blue shifted. People on Earth would see the ship's signals red shifted. Receivers must chase drifting frequencies. Time dilation stretches conversations. A short message exchange for the crew can span years for people on Earth. You could keep a link with careful planning, but it would be thin, delayed, and fragile. The trip would be lonely in a very literal way. Even the way speeds combine protects the limit. If two beams move toward each other at 99% of light speed, you might add them and expect almost twice light speed. Relativity uses a different rule. When you do the correct velocity addition, the relative speed is still below light speed. No clever setup lets any observer watch an object tear past faster than light. The math matches every collider we have built. It is one of the reasons data from head-on collisions remains sensible instead of breaking causality. Beneath the engineering lies a basic lesson about order. The speed of light shapes cause and effect. It sets the range of influence for any signal. It also knits space and time into a single fabric. In this view, you can think of your motion as spread between space and time. When you sit still in space, you move through time quickly. As you move faster through space, your personal flow of time slows. This budget is fixed by the structure of space-time. To move through space at light speed, you would have to spend your entire budget there and leave nothing for time. For matter, that means your own time would stop, which is not a state massive objects can take on. This gives a quiet way to picture things. Everything travels through space-time at the same overall rate set by the speed of light. Massive objects spend most of that rate moving through time, with only a bit spent on motion through space. Light spends all of it on space, with none left for time. The idea is simple enough for a sketch and solid enough to guide real calculations. It is not a trick of words, it is the geometry that keeps physics consistent for all observers. Vacuum itself adds one last pushback. What we call empty space still seethes with brief, virtual particle pairs. An observer who speeds up, who feels acceleration, can, in principle, detect a faint warmth known as the Unruh effect. The temperature grows with acceleration. For normal rockets, the effect is far too small to matter. For extreme, sustained accelerations aimed at near-light flight, it becomes one more source of radiation and heat the ship must dump. It does not build a literal wall of fire, but it reminds us that acceleration carries thermodynamic costs that cannot be wished away. Gravity is part of the ledger too. Energy and mass both curve spacetime. As kinetic energy climbs, the gravitational footprint of a system grows. Spread out over a ship and a long exhaust plume, that effect is tiny. Focus enough energy into a very small space and, in principle, you could form a horizon. Thought experiments explore this with ideas like the hoop conjecture. In practice, our engines are many orders of magnitude too weak and too diffuse to come near that state. Still, the lesson is steady. Energy has weight. Weight curves space, and piling up energy to chase light speed can change the stage you run on. Synchrotron losses, the stubborn Higgs-set mass, the rocket equation's exponential squeeze, the harsh rain of interstellar gas and dust, quantum tunneling that complicates rather than rescues, red-shifted and blue-shifted links that thin with speed, velocity addition that blocks clever cheats, space-time's fixed budget, the faint heat of acceleration, and gravity's response to concentrated energy, all these pieces point the same way. The limit is not a single lock you can pick. It is a network of locks that share the same key idea: keep information moving in order, keep cause before effect, and keep the universe readable to every observer. In 2012, experiments at CERN confirmed the particle linked to mass, the Higgs boson. The result fit a simple picture. A field fills all of space, and particles moving through it feel a kind of drag, not a sticky syrup you could bottle, but a background that gives them inertia. The stronger the interaction with this Higgs field, the more mass a particle has, and the harder it is to push. Photons, the particles of light, do not couple to the Higgs field in the same way, so they carry no rest mass and can cruise at the universe's top speed. Everything else feels that background to some degree and must stay below the limit. The rule is not a mere traffic law. It is part of how reality is built. Neutrinos show what almost looks like in nature. These ghost-like particles slip through matter with hardly a touch and carry only a tiny mass, far smaller than an electron's. When a star in the Large Magellanic Cloud collapsed in 1987, detectors on Earth saw a burst of neutrinos a few hours before telescopes caught the light. The neutrinos did not outrun photons. They escaped the star's dense core immediately, while light took time to fight its way out of the churning layers. Because neutrinos do have a non-zero mass, their speed falls just shy of light speed. Their small mass lets them get very close. It never lets them arrive first, over empty space. Turn that lesson toward travel, and the numbers become human. Suppose a craft could reach 1/10 of light speed, far beyond anything we can build today. The trip to Proxima Centauri would still take more than 40 years as measured from Earth. A crew would need food, water, life support, radiation protection, and a system that can run for decades. Machines would age, materials would fatigue, people would too, and that is only to reach our closest star. The Milky Way's disk spans about 100,000 light years. At 1/10 of light speed, crossing even a single galactic arm would take a lifetime stacked upon a lifetime. Engineered materials have tempted us with odd tricks of light. Metamaterials can bend light the wrong way, producing a negative refractive index, and other media can slow light to walking speed by passing the energy along from atom to atom. These effects change how light moves inside matter, not what the ultimate limit is in empty space. The speed of light in vacuum remains the cap on how quickly information can spread. If you change the medium, you change the local traffic rules, but you do not move the fence at the edge of the field. The universe's own background puts its thumb on the scale at high speed. The cosmos glows faintly with microwave light left from the Big Bang. At ordinary speeds, the cosmic microwave background is a cold, harmless bath. Boost yourself to speeds with many nines after the decimal, and the Doppler shift in your direction of travel squeezes those microwaves into hard radiation. What began as a soft afterglow turns into a forward-facing storm of X-rays and gamma rays. Calculations show that at 99.9% of light speed, the dose would be severe and fast. The sky itself becomes hazardous. Exotic phases of matter have not broken the rules either. Time crystals, observed starting in 2016, are systems whose pattern repeats in time under a steady drive, the way a normal crystal repeats in space. They look, at first glance, like little engines that could run forever. Look more closely, and you find they still obey thermodynamics and still respect relativity. Their unusual rhythm does not allow signals to outrun light or machines to sidestep the second law. A quantum twist, known as the Zeno effect, offers a different kind of caution. In quantum mechanics, repeated checking of a system can hold it in place, like watching a pot so often that it never seems to boil. No one uses this to stop a rocket. That is not how flight works. But the idea signals something important. At extreme acceleration, a system interacts more with the restless quantum vacuum. In some models, this constant jostling acts like frequent measurements that resist smooth change. It is not a magic barrier, but it is another way the small-scale rules add friction when you try to push too close to the limit. Nature runs high-energy trials that we can watch across the universe, around supermassive black holes, magnetic fields, and fierce gravity, launch twin jets of particles that approach light speed. These beams travel for thousands of light years and shine across the spectrum. Sometimes, due to geometry and light travel time, they even look like they move faster than light on the sky. That illusion fades when you do the math correctly. The true speeds stay under the limit. If the combined power of a black hole and a whole galaxy cannot drive matter past light speed, our engines will not either. There is also a rule about messages, not just machines. Information cannot outrun light. That statement protects cause and effect. Break it, and you could send a signal that arrives before it was sent for some observers. Then, what caused what loses meaning. The universe avoids that breakdown by keeping all signals within the same top speed. Even light can be tamed without breaking the rule. In ultra-cold gases called Bose-Einstein condensates, teams have slowed light pulses to a crawl and even stopped them. What really happens is that the medium soaks up the pulse, holds its pattern in atomic states, and later releases it. The front edge of a brand new signal, the part that marks the start of information, still cannot move faster than light in vacuum. The trick changes storage and retrieval. It does not change the fundamental speed limit. Some deep ideas try to connect the speed limit with information and geometry. The holographic principle proposes that the information inside a region can be encoded on its boundary, like a three-dimensional world described on a two-dimensional screen. From this view come bounds that limit how much information you can pack into an area and how quickly it can be processed or transmitted. The speed of light then looks less like a number pulled from a hat and more like the natural pace set by spacetime's bookkeeping of information and entropy. Dark matter and dark energy set the stage for what we can reach. Dark matter holds galaxies together. Dark energy pushes space apart. The push is winning at large scales. Distant galaxies are carried away by the expansion so quickly that their light will never reach us. Others, still visible today, will drift beyond a horizon we cannot chase. Even a perfect ship, cruising at light speed, would be locked out of most of the cosmos, simply because space keeps stretching between here and there. Quantum entanglement sometimes seems to laugh at limits. Two particles prepared together can show strong correlations, even if they are later far apart. Change one, and the other's state is instantly related. That sounds like a message, until you notice that each result is random. Only when both sides compare notes using plain, slower-than-light communication do the patterns appear. Entanglement gives you instant coordination without control. It keeps causality safe, while still revealing something deep and strange about how quantum states are shared. Thread these pieces together and a single picture stands out. Mass comes from a field woven through space. Tiny mass particles can only approach, never reach, the limit. Practical travel times, even at optimistic speeds, ask for lifetimes. Fancy materials and cold atom tricks reshape how light behaves in matter without moving the universal fence. The microwave glow of the early universe turns fierce when you dash into it. Exotic phases respect the same boundaries that ordinary matter does. Quantum rules add friction rather than shortcuts. Black hole engines can push particles near the limit, but never past it. Messages stay under the cap to protect cause and effect. Information itself seems tied to area and to a maximum pace. And the largest scales of the universe recede faster than any ship could hope to follow. All these roads point to the same conclusion. The speed of light is not just about how fast beams move. It is about how reality organizes change, sets the flow of information, and keeps the story of the universe consistent for every observer. One way to see why light's limit matters is to look at what would happen if it were different. If light moved infinitely fast, electrical forces would act with no delay. Electrons would snap to new positions instantly. Atoms would not settle into stable shells. Bonds would not hold. Chemistry would either finish at once or never start. Life depends on reactions that unfold at a measured pace, with signals that take a tiny, finite time to move across molecules and cells. The value of the speed of light is part of that balance. Nudge it far, and the universe turns unfriendly to complexity. Neutron stars underline the point from another angle. These are collapsed stellar cores, packed so tightly that a teaspoon would weigh as much as a mountain. Some of them beam radio waves like lighthouses as they spin. We call them pulsars. The fastest spin hundreds of times each second. One record holder turns about 700 times per second, with its equator moving at roughly a quarter of light's speed. Add more spin, and the outer layers would fly off. Even gravity, billions of times stronger than Earth's, cannot hold matter together if the edges try to move too fast. Nature sets a ceiling long before the ultimate limit comes into view. Black holes add a deeper layer. Near the event horizon, the geometry of space and time tilts inward. To hover there, you would need rockets that keep you from being pulled along by that flow, and the required thrust rises without bound as you approach the horizon. Cross it, and every path forward leads inward. Some proposals in quantum gravity suggest the horizon might be ringed by extreme radiation, a firewall, if certain patterns of quantum entanglement break down. The details are unsettled, but the theme is steady. The speed limit is not just about light in a vacuum. It is about how space-time itself carries information and energy. Hypothetical objects called cosmic strings paint still another picture. If they exist, they would be thin defects in space-time, like seams left over from the early universe as it cooled. A loop of string, or two strings, passing in just the right way, might, in certain models, allow paths that loop back in time. Each time the math opens that door, causality starts to break. The same calculations that tempt us with shortcuts also breed paradox. Signals arriving before they were sent, events without causes. The consistent answer has been to shut those doors, either by forbidding the needed conditions or by showing that quantum effects destroy the setup before it can be used. Quantum experiments often look as if they are teasing the rules, but the details keep causality safe. In the delayed choice quantum eraser, you can choose to keep or erase which path information about a photon after it has already traveled through an apparatus. The final pattern on a screen seems to depend on a later choice. It does not let anyone send a message into the past. The trick only shows up when you sort the data after the fact with slow, normal communication. No information moves faster than light. The statistics line up only when both sides are compared in the usual way. At the tiniest scales that physics can talk about, the Planck scale, around 10, -35 meters, quantum effects of gravity may make spacetime frothy or discrete. In that picture, you can imagine a maximum rate at which change can ripple across this grainy fabric. The speed of light then looks like a refresh rate for reality, the fastest pace at which neighboring bits of spacetime can update each other without losing consistency. Whether spacetime is truly discrete or not, the limit plays the same role in the equations we trust at larger scales. The idea of a false vacuum pulls the discussion into existential territory. Our universe might sit in a state that is stable enough to last, but not the lowest possible energy. If a lower state exists, a tiny bubble of it could, in theory, form somewhere and expand, changing the rules of physics inside it as it grows. Calculations say such a bubble would race outward at essentially the speed of light. There would be no warning and no way to outpace it. The same limit that shapes every signal also sets the boundary for how fast a global change could spread. Nature provides stress tests for the limit in the most violent events we see. Gamma-ray bursts send out brief, intense flashes and drive jets whose particles move at more than 99.999% of light speed. The beams travel across billions of light years and still stay under the cap. That is with engines powered by the collapse of massive stars or by the merger of compact objects, turning huge amounts of mass into energy in seconds. Even then, the last fraction toward light speed never arrives. Special relativity has a tool called rapidity that helps keep track of speeds in this regime. Instead of adding velocities the way we do at slow speeds, we add rapidities, which stack neatly even when speeds are high. Rapidity can grow without limit, but when you convert it back to ordinary speed, you always get a number below light speed. This language change does not weaken the rule. It makes the rule simple to apply. Ideas for warp travel try to step around the barrier by moving space-time rather than a ship. The Alcubierre metric is a solution to Einstein's equations, where space in front of a bubble contracts and space behind it expands, carrying the bubble forward. Inside the bubble, nothing locally breaks the speed limit. The trouble shows up in the materials list. Building and steering such a bubble seems to require matter with negative energy density, something we have not found in usable form. Quantum physics also places severe limits on how negative energy can be arranged and for how long. When researchers fold those limits in, the needed conditions look unstable or fantastically out of reach. Every clever version runs into a new wall, not a single wall, but a fence of them. There is a human scale way to tie these threads together. The speed of light shapes how atoms hold, how stars can spin, how horizons trap, and how signals move. It organizes timing in quantum experiments so that odd correlations never turn into backwards messages. It shows up as a maximum pace, whether we look at tiny scales where gravity and quantum rules may meet, or at cosmic scales where the universe expands. It sets how fast doom would spread if the vacuum changed, and how fast hope could travel if we ever launched a message to distant minds. The anthropic view adds a quiet coda. We live in a universe where this limit has just the right value to allow stable atoms, slow enough chemistry, and long-lived stars. Those are the conditions that give time for complexity to grow. If the limit were very different, no listeners would be here to wonder about it. That is not a proof. It is a reminder that the number we call C sits inside many balances at once. When we look at pulsars, we see what happens when matter tries to brush the limit and cannot. When we watch black holes, we find the limit woven into the horizons, very meaning. When we test quantum ideas, we find boundaries that protect cause and effect. When we stare at the biggest and smallest pictures we have, we keep finding the same ceiling. All along, the universe remains consistent. Faster-than-light tricks keep turning into illusions that vanish under careful accounting. Paths that promise shortcuts curl into paradox or crumble under quantum back reaction. Mathematical knobs that can go to infinity still map onto ordinary speeds that stop at the same place. The lesson is not that the cosmos lacks imagination. It is that a single rule threads through many domains, keeping the story readable from every vantage point. The speed of light is that rule written into the grain of reality, shaping what can happen, and how, and in what order, everywhere from atomic labs to the edge of the observable sky. Stephen Hawking outlined a guardrail he called chronology protection. The idea is simple to state. The laws of physics keep time travel from working at large scales. Faster-than-light travel would open loops in time, called closed, time-like curves, where an event could circle back and affect its own cause. Hawking argued that quantum effects would blow up the energy near any would-be time machine, making the setup tear itself apart before a paradox could form. The fix is not a patch added later. It is a natural consequence of quantum fields responding to extreme space-time geometry. If exceeding light speed builds a path to yesterday, the same physics that allows fields and particles to exist raises an infinite red flag. Even matter in its strangest forms does not slip the leash. Superfluids flow without friction. Superconductors carry current with zero electrical resistance. Both arise when many particles act as one coherent quantum state. Helium-4 becomes a superfluid near absolute zero. Certain metals become superconductors when electrons pair up and move collectively. Their behavior looks like it should beat ordinary limits, yet their signals and disturbances still travel no faster than light. Phase stiffness in a superfluid can transmit motion quickly, but not instantly. A superconductor's perfect conductivity removes loss, not delay. Information and energy still need time to cross a distance. The speed limit holds even when materials act nothing like everyday stuff. There is a useful way to think about this limit that comes from computing. Imagine the universe as a machine that updates its own state. Each interaction is a little step of processing. The speed of light then plays the role of a global clock rate, the fastest pace at which cause can lead to effect, the fastest any update can propagate. Asking for faster-than-light signals is like asking a processor to deliver outputs between ticks of its clock. The request is not just difficult, it has no meaning within the rules that define the system. Quantum computers change what can be done inside the tick, but not how fast a tick can spread across space. Superposition and entanglement let them explore many possibilities in parallel and, for certain problems, reach answers with far fewer steps. Yet those quantum advantages never allow a message to outrun light. Entanglement gives strong correlations, but no controlled signal. When a quantum computer finishes a calculation, the result still has to be read and sent through ordinary channels. The universe allows speed-ups in logic. It does not allow shortcuts in communication. Time itself changes pace in gravity. Clocks higher above Earth's surface tick faster than clocks on the ground because gravity is weaker up there. GPS satellites feel both this gravitational time dilation and the slowing due to their orbital speed. The altitude effect adds roughly 45 microseconds per day to their onboard clocks. Their motion subtracts a smaller amount. Engineers account for both pieces, or the system would drift by kilometers in a single day. Take that idea to a black hole, and the effect becomes extreme. As you hover near the event horizon, your clock slows as seen from far away. At the horizon, outward paths through space-time become impossible. For a distant observer, time at that surface appears to stall. Velocity, time dilation, and gravitational time dilation act together in ways that make any simple plan to just go faster fall apart. Nature's particle accelerators underline the same message. The most energetic cosmic rays reach Earth with mind-bending energies. One famous event carried the energy of a baseball thrown at about 60 miles per hour, packed into a single proton. Its speed had 22 nines after the decimal, when written as a fraction of light speed. That is unimaginably close, but not equal. The final gap did not close, even though the particle had more energy than any machine we can build. If supernova shocks and black hole jets cannot push a proton to light speed, our engines will not either. In the strongest magnetic fields near neutron stars, empty space behaves like a material. Quantum electrodynamics predicts vacuum birefringence. The vacuum becomes polarized so that light with different polarizations travels slightly differently. Observations near magnetars neutron stars with magnetic fields billions of times stronger than anything on Earth show hints of this effect. Even there, light still respects the same top speed. The fields change how light moves. They do not raise the speed limit. The expansion of the universe adds another quiet boundary. Studies of distant supernovae showed that space is expanding faster and faster, a discovery honored with the 2011 Nobel Prize in Physics. As the expansion speeds up, more galaxies cross a threshold where their light can never reach us. They are not moving through space faster than light. Space between us and them is stretching too quickly. The region with which we can ever exchange signals is shrinking in a practical sense. Even a perfect ship cruising at light speed would find most of the universe permanently out of reach. Rotation twists space-time as well. General relativity predicts frame dragging. A spinning mass drags the nearby space-time around with it. The Gravity Probe B mission measured this effect around Earth. Near a rotating black hole, frame dragging becomes so strong that there is an ergosphere outside the horizon where all paths are swept forward. You cannot stand still relative to the distant stars. From far away, space itself seems to be pulled around faster than light in that region. Locally, though, no object outruns light. The rule is local and absolute. In your neighborhood of space-time, nothing with mass passes a light beam. The strong nuclear force shows how some barriers are baked deep into the rules. Quantum chromodynamics binds quarks into protons and neutrons. Try to pull two quarks apart, and the force between them grows. Add more energy, and you do not free a quark. You create a new quark-antiquark pair, leaving you with two bound systems instead of one. This confinement is not a technical obstacle. It is a principle. In the same spirit, no amount of energy frees a massive object from the speed limit. Energy changes states. It does not dissolve the rule. Electromagnetism itself points to the same constant. Maxwell's equations tie changing electric and magnetic fields together so that a ripple in one makes a ripple in the other. Work through the math, and the ripples move at a speed set by constants that describe how electric and magnetic fields work in vacuum. That speed is c, the same number measured by experiments. Tinker with c, and you tinker with the nature of the fields. Change the fields, and you change chemistry. Change chemistry, and stars, planets, and life look nothing like what we know. The value is not isolated on a chart. It is woven through many layers of physics. Binary pulsars provide a long, careful test of gravity's timing. In systems like the Hulse-Taylor pulsar, two neutron stars orbit each other, and slowly spiral inward. They lose energy at a rate that matches the prediction for gravitational waves radiating away ripples in spacetime that carry energy. The timing agrees with general relativity across decades of observation. Those ripples propagate at the speed of light. The same conclusion reached when gravitational waves and light from a distant neutron star merger arrived at Earth within seconds of each other after traveling for over 100 million years. Gravity's updates cross space at sea, not faster. Across these examples, the picture is consistent. Try to make a time loop, and quantum fields push back with growing energy. Build quantum matter with perfect flow or perfect current, and signals still move undersea. Speed up logic with qubits, and messages still wait for light. Move clocks into weaker gravity and they run fast. Drop them toward a horizon, and they slow. Hurl protons with star-sized engines, and the last decimal places remain out of reach. Twist space with rotation, and it still respects local limits. Pull quarks, and you create more particles. Not freedom. Write down the equations for fields, and C drops out as the natural speed. Watch neutron stars lose energy and you read gravity moving at C in the timing. Seen this way, the speed of light is less a ceiling you bump against and more the pace that keeps the universe readable. It times the steps that let causes lead to effects. It sets the rate at which fields can tell their neighbors that something has changed, and it limits what any machine can do between one moment and the next. Every domain we can probe materials that act like one giant wave, clocks in curved space-time, particle beams from distant explosions, and the quiet math of field equations comes back to the same limit and the same reason for it to exist. Proper time is the time a clock carries along its own path. It measures the aging of an object as it moves through space-time. For anything with mass, proper time always advances. Each heartbeat, each tick, adds to that total. For light-like paths, the proper time between emission and absorption is exactly 0. Light has no rest frame, so we avoid saying what a photon experiences. But the mathematics is clear. Along a light-like trajectory, there is no passage of proper time at all. Reaching light speed would mean sliding onto a path where your own proper time stops, which massive objects cannot do. Time dilation slows a traveler's clock as speed rises. Proper time makes the limit explicit. There is no next tick left at C. Ultra-intense lasers show how hard we push against the rules and how the rules hold. Facilities that focus short pulses to extreme intensities can tear pairs of electrons and positrons out of the vacuum field, converting light's energy into matter. In these experiments, electric fields rival those inside atoms and briefly approach the theoretical scale, where empty space becomes unstable. Even so, the particles born in the flash still obey relativity. You can hurl them to huge energies. You can make the vacuum itself yield pairs, but you cannot drive a charged particle past C. The limit does not crack when the laboratory reaches its loudest settings. Black holes present an edge case that still respects the boundary. Hawking radiation arises from quantum fields near the event horizon. In simple language, virtual pairs form. The black hole's gravity can separate them so that one member escapes while the other falls in, reducing the hole's mass. A more careful view treats it as particle creation by curved spacetime. Either way, the story keeps the same pace. The escaping quanta stream away at sublight speeds in their local frames, and no signal outruns C. Even at a horizon where escape paths narrow to nothing and geometry is most extreme, the speed limit is not broken. Physicists watch for any cracks in the broader symmetry called Lorentz invariance, the statement that the laws of physics look the same to observers moving at constant speeds. If those laws shifted with energy or direction, We might see tiny delays that depend on frequency in gamma rays from distant bursts or subtle anisotropies in precision lab tests. Across many experiments and astronomical baselines, the result is consistent. No deviation has shown up. The timing of high-energy photons, the behavior of atomic clocks, and interferometer measurements all line up with a single, unchanging speed. The rules appear the same, no matter how fast you cruise or which way you turn. Information and entropy add a quiet barrier of their own. Erasing one bit of information has a thermodynamic cost. It raises entropy. Describing a fast, highly energized object requires tracking more and more details of its quantum state. As speed approaches c, the bookkeeping swells without bound. More energy, more modes, more correlations to specify and stabilize. A world that allowed matter to cross c would demand an infinite information density to describe and control that crossing, which collides with the second law. The limit keeps the accounting finite and the arrow of time intact. Engineering realities bring those abstractions down to the workshop. The International Space Station circles Earth at roughly 7.7 kilometers per second, only a few thousandths of a percent of light speed. Building and operating it took many launches, an international partnership, and decades of work. 1% of light speed is about 3,000 kilometers per second. Kinetic energy scales with the square of speed, so each kilogram at that pace carries on the order of 100,000 times more kinetic energy than in low Earth orbit. That is not a matter of better fuel valves or lighter wiring. It is a different scale of energy, structure, and heat rejection. Between what we can do now and even a single percent of c lies a gulf measured in orders of magnitude. Gravity we cannot see adds to the navigation problem. Most of a galaxy's mass hides in a dark halo that extends far beyond the visible disk. It shapes, orbits, bends light, and sets up gentle but real gradients in the gravitational potential. A craft moving for decades, near a percent of light speed, would cross that lumpy landscape, feeling tiny tugs that add up. We map dark matter statistically from galaxy rotations, lensing arcs, and cosmic background patterns, but we do not know the fine-grained structure along any particular line of travel. Steering precisely through an unseen sea becomes part of the problem. Plasmas introduce another set of limits. As speed rises, a fast-charged stream compresses its electric and magnetic fields into a narrow cone ahead and around it. In a vehicle or beam, those fields can couple to the plasma of the exhaust or to the tenuous gas outside, exciting waves that feed on the flow. Known instabilities to stream, wobble, and others can grow, shake energy out of the motion, and hammer materials with oscillating currents and fields. At modest speeds, good design damps these modes. At relativistic speeds, the growth rates and couplings intensify. The system begins to talk to itself in non-linear ways that are hard to tame, threatening electronics and structure from the inside. Even empty space contributes. The Casimir effect shows that the vacuum has structure. When two conducting plates sit very close together, quantum fluctuations between them are altered, producing a small force. Change the motion or geometry fast enough, and you can stimulate related effects, turning vacuum fluctuations into real photons, a dynamical Casimir effect. The same family of ideas has led theorists to explore whether a rapidly moving or accelerating body feels an effective drag from the vacuum, a kind of quantum friction. For ordinary speeds, this is immeasurably small. As acceleration and field strengths rise, the corrections grow. They do not hand you a speed boost. They add another term to the resistance you have to fight. Signals from across the universe keep checking the same constant. Fast radio bursts, millisecond flashes from distant galaxies, arrive stretched by the plasma they pass through. Lower frequencies come later. After correcting for that known dispersion, the pulses line up in time with an accuracy that leaves little room for different speeds in vacuum. Radio, visible, X-ray, and gamma-ray photons all track the same C to high precision. Over billions of light years, the universe has not found a way to make one color outrun another. Time dilation makes some voyages possible in principle while separating travelers from their origin in practice. At cruising speeds with 4 nines after the decimal, a trip to the Andromeda Galaxy takes millions of years as Earth measures it, but only tens of thousands of years on the travelers' clocks. Push the speed higher, and the crew's proper time shrinks further. A round trip would deliver them to an Earth millions of years older than the one they left. The separation is not only distance, it is epoch. Communication during the journey would crawl. Any return would feel like stepping into a different branch of history. Put together, these threads draw the same outline. Proper time marks the impossibility of living on a light-like path. Extreme lasers can create matter from light, but cannot push matter beyond light. Hawking's calculation anchors the limit at horizons rather than loosening it. Tests for Lorentz symmetry cracks keep coming back clean. Information theory and thermodynamics guard against infinite descriptions. The step from orbital speeds to percent of C flight multiplies energies to daunting levels. Invisible gravity complicates steering, while plasmas and their instabilities threaten control. Quantum vacuum effects add small but principled sources of resistance. Celestial pulses arrive with the timing of a single, shared speed. And the deeper you plan a relativistic voyage, the more time itself becomes the main divide. The speed of light stands not as a negotiable target, but as the tempo that keeps physics, communication, and history in a consistent order. Metamaterials show how far we can bend light without breaking the rules. Engineers stack tiny structures smaller than a wavelength so that waves weave through in unusual ways. In some samples, light bends backward, making a negative refractive index. In others, pulses crawl slower than a walking pace. And in carefully tuned gases, the energy of a light pulse can be stored and later released, appearing to stop. These tricks change how a wave's crest moves, phase velocity, or how a pulse spreads, group velocity. They do not change the front velocity, the very first ripple that carries new information. That leading edge still travels no faster than light in vacuum. The effect is like steering a crowd, so the pattern shifts while the first runner still obeys the speed limit at the track's edge. Mass itself points to the same limit through the busy life inside a proton. Protons and neutrons are not quiet billiard balls. They are seas of quarks, stirred by the strong force and glued together by gluons. Most of a proton's mass does not come from the tiny rest masses of the quarks, but from the roaring motion and fields of these virtual gluons and quark-antiquark pairs. As you drive a particle toward light speed, this cloud of virtual activity thickens and the bookkeeping of energy and momentum grows. The relativistic mass language is old-fashioned, but the practical meaning is clear. More energy goes into motion and fields that become harder and harder to push. The closer you get to the limit, the more the internal storm contributes to the resistance. Astronomers check the constancy of the rules with cosmic clocks. Millisecond pulsars spin with a steadiness rivaling atomic clocks. By watching their ticks over years and comparing many sources spread across the sky, teams can test whether fundamental constants have drifted. The timing allows tiny shifts to show themselves as changes in arrival patterns. So far, the data say no. If anything has changed at all, it is smaller than our current sensitivity by an enormous margin. Light speed looks the same across vast distances and long stretches of time, tying today's laboratory physics to the early universe with impressive precision. Acceleration alone creates its own horizon. A steadily accelerating observer finds that there is a boundary behind them beyond which signals can never catch up. This is the Rindler horizon. As the thrust increases, the horizon draws closer, carving away more of the past you can ever see. The picture offers a simple intuition. To jump to light speed instantly would ask for infinite acceleration, and the horizon would press right against you, sealing you off from all communication behind. Even without moving faster than light, trying to brute force acceleration builds walls in space-time that cut you off from information. Quantum field theory adds heat to that story. An accelerating observer does not see empty space as empty. Instead, they perceive a warm bath of particles, Unruh radiation whose temperature rises with acceleration. For normal rockets, this temperature is tiny, far beyond any practical concern. Push harder and the bath grows hotter. In thought experiments where acceleration becomes extreme, the vacuum can spit out particle-antiparticle pairs more readily, and the act of pushing begins to feed a cascade of radiation. The details are still a topic of active theory, but the sign points the same way. Acceleration carries a cost that grows faster than your reward as you chase the limit. Information bounds suggest a deeper reason for that cost. The holographic viewpoint says that the maximum information inside a region scales with its surface area, not its volume. That leads to limits on how much information can be stored, processed, or transmitted in a given space and time. Driving a ship and its shielding, controls, and life support toward light speed means stabilizing and updating an ever more complicated quantum state against noise and radiation. If there is a hard cap on information density and processing rate per area, then there is a built-in ceiling on how finely you can control a system under extreme conditions. The limit on speed starts looking like a limit on information flow written into geometry itself. Even the emptiest places have something to say about all this. Cosmic voids, the wide, dark regions between galaxy clusters, are not truly empty. Quantum fields live everywhere, setting a baseline wiggle for space. At modest speeds, these fluctuations average out. At relativistic speeds and under strong acceleration, the way your craft couples to those fields changes. Tiny forces that would normally cancel can become noticeable. Small instabilities can get a foothold. We do not expect a neat vacuum wind, but we do expect new channels for energy to leak and new ways the environment can push back as you drive fast through the deep. Meanwhile, the sky's largest scale story keeps shrinking our practical goals. The universe's expansion is accelerating. Beyond a certain distance, galaxies are carried away so quickly by the growth of space that their light will never reach us. New regions cross that horizon as time goes on. Even a perfect vehicle that rides at light speed would be confined to a bubble that, while huge, excludes most of what exists. The limit is not only local, it is cosmic. The map we could ever explore is bounded by the same constant that times a lab laser. Some recent ideas suggest that time itself may be an emergent effect. In these views, the flow we feel is a pattern arising from correlations among quantum systems. If that is right, the speed of light would be the fastest pace at which such correlations can knit a consistent sense of before and after. Trying to outrun C would not just fail. It would reach outside the conditions that make time meaningful at all. The idea is still being shaped and tested, but it frames the speed limit as the cadence that lets events line up into history. Forces behave differently at high speed, but they do not hand out loopholes. Electromagnetism is carried by photons and already reaches across space at light speed. The weak force uses heavy W and Z bosons, which move subliminally and give short-range effects like radioactive decay. As you push matter to relativistic speeds, the way these forces combine can change. Decay rates measured in the lab slow down in the lab frame because the particle's time slows. In the particle's own frame, the intrinsic rate is the same. Chemical bonds can look different when fields transform between frames, but local chemistry still follows the same rules. The balances that let atoms hold remain, even as radiation and field strengths turn the surroundings harsh for any real object. Astrophysical jets display nature's best attempt at a cosmic accelerator. In the cores of active galaxies, twisted magnetic fields snap and reconnect in a process called relativistic reconnection. The snap flings particles to enormous energies and focuses them into beams that shine across the spectrum. Maps of these jets show patterns that move nearly at light speed. Sometimes they appear to move even faster due to the way light travel times play tricks with perspective. Careful measurements sort the illusion from reality and keep the speeds under C. The systems add more energy and get closer, but the approach is asymptotic, a curve that keeps nearing a line it never crosses. Limits touch our inner life too. Thought is electrical activity riding networks of cells. Signals hop across synapses and travel along fibers at speeds set by biological design and electromagnetism. Some speculate that quantum effects might influence how brains work. Whether or not that turns out to matter, any such processes still sit under the same roof. No message outruns light. In that sense, the cosmic limit may also cap how quickly any mind, biological or artificial, can sense, decide, or feel a moment pass. Exotic materials reinforce the theme from another angle. Topological insulators and related systems allow current to flow along their surfaces with unusual stability, while the interior stays insulating. Their edge channels are robust against many kinds of disorder, and their electrons seem to glide without scattering. Even here, signals do not leap ahead of C. The robustness protects against noise. It does not rewrite the speed at which information can be launched from one point and caught at another. Gravity provides clean timing tests over cosmic baselines. Light from a distant quasar can bend around a galaxy in its path, producing multiple images. Each light path has a different length and travels through different gravitational potentials, so the images flicker at slightly different times when the quasar varies. By modeling the geometry and measuring the delays, astronomers can check whether different energies of light keep the same pace and whether gravity's influence matches expectations. Across billions of light years, the answer keeps coming back the same. The speed is constant, and the rules match what we measure nearby. Quantum measurement adds one more quiet clamp. The quantum Zeno effect says that frequent observation can hold a system near its starting state by collapsing its spread over and over. At high speeds, a particle's interactions with fields and with its own radiation amount to a kind of constant probing by the environment. The more intense the coupling, the more the system resists smooth change. No one can use this to nail a ship in place or to goose it past the limit, but the intuition is useful. As you turn every knob to chase C, the universe checks your system more often. Each check adds friction to orderly acceleration and pushes back on attempts to change too quickly. Thread these pieces in order, and they tell a single story. We can steer waves with metamaterials, but the bit that carries news never arrives before C. The mass of ordinary matter is mostly motion and fields bottled by the strong force, and that storm becomes harder to push as speed rises. Pulsars tick out a verdict of constancy across time. Acceleration builds horizons that hide parts of the past. Push too hard, and the vacuum warms around you. Information bounds cap how fine-grained control can become in a finite area and time. Voids are not empty to a fast traveler. Quantum fields give them texture. The universe's growth puts most of everything forever out of reach, regardless of any engine. If time is an emergent pattern of correlations, C may be the fastest beat that can sustain that pattern. Forces transform between frames, but still follow the same law set. Jets in distant galaxies race toward the limit and only ever approach. Thoughts ride signals that are themselves limited by the same constant. New phases of matter give stability, not shortcuts. Gravitational lenses test light's timing across cosmic distances and find the same value. Quantum systems probed too often resist change, hinting that the environment itself enforces gentler pacing as you try to sprint. Every corner, examine the lab, the vacuum, the galaxy. The mind keeps pointing back to the same constant and the same boundary. The speed of light marks how fast influence can spread, how quickly information can be shared, and how events can stitch themselves into a consistent order. It is not a line we cross with better tools. It is the frame that tools must live within. Gravitational waves and light keep time together across the deep. When two neutron stars spiraled into each other about 130 million light-years away, the ripples in space-time reached Earth, almost at the same moment as the light from the blast. After traveling for more than 100 million years, the difference was only seconds. That near tie tells us something simple and strong. Gravity's changes spread at the same pace as light. It is not just photons that honor the limit. The geometry of space-time itself does. Some ideas in quantum gravity suggest an even deeper picture. Space and time may not be smooth and fundamental. They might be built from fine, discrete elements, like threads in a fabric. In loop quantum gravity, areas and volumes come in tiny chunks, and the weave sets how geometry behaves. In such a world, the speed of light is like a maximum signal speed for the weave, similar to the fastest speed a disturbance can cross a solid, which we call the speed of sound. The analogy is not perfect, but the message is clear. If space-time emerges from more basic parts, c is the fastest rate at which those parts can pass along change without breaking the pattern. Black holes bring the speed limit and quantum information into the same frame. The event horizon is where escape becomes impossible, because the outward path you would need to take would have to outrun light. Some theories, trying to keep quantum information from being lost, propose a firewall of very high energy quanta at or near that boundary. The details are debated, but the setting is precise. The boundary lies where escape speed equals c, and the arguments about information all happen on that edge. Whether firewalls exist or not, the paradox itself shows how the limit, quantum rules, and gravity meet in one place. On the larger scales, the universe grows structure under the same limit. Gravity pulls matter together to form strands and nodes, the cosmic web of filaments, clusters, and superclusters. But gravity does not act instantly at a distance. Its changes move at light speed. Over the age of the universe, only regions that could hear each other at that pace had time to settle into the patterns we see. If influence could race infinitely fast, the web would look different, smoother in some ways, more rigid in others. The shapes we map tell us that assembly took time, and that the messages between distant patches of matter never moved faster than c. Vacuum decay sits at the edge of physics and philosophy, but still keeps to the pace. If the Higgs field, which helps set the masses of particles, is sitting in a state that is stable but not truly lowest, a bubble of a lower state could, in theory, form. The laws inside that bubble could differ from our own. The math says such a bubble would expand at light speed. It would not be a fireball we could outrun. It would be a boundary crossing the universe as fast as any cause can spread. Even a scenario that dramatic uses the same limit as its ruler. Light can push and pull on matter, and engineers now control this dance with great care. In optomechanical experiments, tiny mirrors and beams are tuned so finely that the motion of a mechanical object can be cooled to its quantum ground state, the quietest possible motion allowed by quantum mechanics. We can watch quantum effects in objects large enough to see with the eye. Yet the information we write with light in these systems still moves at light speed, and the vibrations in the device still carry signals at their own finite speeds. The boundary separates what is possible from what is not, even when the classical and quantum worlds meet. Complexity itself seems to need a limit to exist, for parts to work together, to compute, to grow, to think. Signals must travel between them and return. Those signals need time. As speed through space rises towards c, time for the traveler slows. At light speed, proper time on that path would be 0. A process cannot unfold if its local time does not pass. That is a gentle reason the universe might keep a finite top speed. Without it, stable, layered, long-lived complexity would have no room to breathe. Nature even hints at error correction built into its rules. Quantum systems are fragile, yet some patterns, like those in certain topological phases, protect information against small disturbances. Theorists draw links between these protective codes and the structure of space-time itself. In that spirit, if a process tried to violate the speed limit, the same stabilizing mechanisms might act like a correction, steering the system back into allowed behavior. It is an analogy, not a finished theory, but it points toward a universe that both permits rich dynamics and guards basic rules. From an anthropic point of view, the value of c is part of a set of numbers that allow a universe like ours. If light crossed space much faster or much slower relative to other forces, the balance among electromagnetism, the nuclear forces, and gravity would shift. Atoms might not hold, stars might not live long, or galaxies might never form. Our particular value is not a random dial setting. It appears inside many interlocking balances that make chemistry, stars, and life possible. Some philosophers go one step further and ask whether a limit like c is not just physical, but logically required. The idea is that any consistent world, where signals carry causes to effects, must have a maximum rate of influence. Without it, different observers could disagree about the order of events, and the logic that supports prediction and explanation would fail. In that view, asking for speeds above c is like asking for a triangle with 4 corners. The request looks sensible in words, but collides with the structure that makes the words meaningful. A different lens comes from the simulation hypothesis. If reality is the output of some underlying computation, then there would be a maximum rate at which the substrate can update. Light speed would be that clock rate made visible in physics, the pace at which information can be written from one place to the next. Trying to exceed it would be like asking software to finish a step before the processor can perform it. Inside the system, faster than the update has no meaning. All these angles can feel distant, but they circle back to what we aim to do. We dream of traveling to the stars. The limit says we will not cross the galaxy the way ships cross an ocean. Yet the same constant protects order. It keeps cause before effect. It lets clocks agree on what after means. Once we account for motion and gravity, it stops messages from arriving before they are sent. It holds the thread that lets stories have a beginning, a middle, and an end. There are practical echoes of these deep ideas everywhere we look. In labs, the tie between gravitational waves and light across 130 million light-years shows that space-time itself updates at sea. In quantum gravity sketches, the speed of light looks like the fastest stitch in the fabric. Near horizons, where escape equals c, arguments about firewalls and information play out right on the line drawn by the limit. Across the cosmic web, finite propagation shapes the patterns that span billions of light-years. Even wild scenarios like vacuum decay obey the same pace. In precision experiments with light and moving mirrors, we see quantum effects without any hint of superluminal signals. When we think about complexity and thought, we find they need time to pass and messages to travel, which requires a top speed less than infinite. One way to picture all of this is to imagine the universe as a vast conversation. Forces, fields, and particles are the speakers. They pass messages across space and time. The speed of light is the conversation's cadence. It keeps the words in order so the story makes sense. From the first galaxies forming out of a smooth glow to a detector on Earth hearing the last shiver of two neutron stars becoming one, the cadence does not slow the story. It makes the story possible. Gravitational waves carry news of the universe's most violent moments. Two neutron stars spiraling together flex space-time itself, sending ripples outward in all directions. When one such merger occurred about 130 million light-years away, detectors on Earth felt the space-time tremor, and almost at the same moment, telescopes captured the light from the explosion. After a journey lasting more than 100 million years, the delay was measured in seconds. That timing is a clean statement about the world. The updates in gravity move at the same pace as light. The limit belongs not only to particles and fields we can see, but to the geometry that holds everything together. Hopes for shortcuts still invite careful study. A warp drive would contract space in front of a craft and expand it behind. A traversable wormhole would act as a tunnel linking two far-off points. Entanglement would seem to stitch distant particles together. Each idea meets the same set of breaks. Warp bubbles need negative energy in quantities that known physics cannot supply, and quantum inequalities forbid arranging for long. Wormholes that stay open demand exotic matter and are unstable when you add realistic effects. Entanglement gives strong correlations, but never a controllable signal. When the math is done and the assumptions are checked, causality stays intact, and the speed limit remains. The limit can feel harsh when we think about what is beyond our reach. The expansion of the universe accelerates, which means many galaxies we see today will drift beyond any chance of contact. Far in the future, observers bound to a single galaxy could look into a dark sky and never know how crowded it once was. Yet, our era sits in a narrow window of visibility. We can still map the cosmic web, weigh clusters, and catch light that left young galaxies when the universe was only a small fraction of its current age. The boundary that keeps us from going everywhere also lets us read the record written in light. Searches for other minds inherit the same rules. If civilizations exist, they face the same ceiling on speed. Empires spanning thousands of light-years with instant communication are stories, not plans. More likely, intelligence lives on islands separated by gulfs of time and distance, sharing messages that take centuries or millennia to arrive. A beacon may be simple and steady, narrowband radio, a pulsed laser, a careful pattern in starlight, because reliability matters more than speed. The limit does not single us out, it applies to everyone. A finite speed for light turns the night sky into a time machine. The moon's glow left a second ago. Sunlight set out 8 minutes earlier. Bright winter stars show scenes from years in the past. Deep sky galaxies display their youth as if in a photo album. With infinite speed, those layers would collapse into a single instant. We would lose the ability to watch galaxies grow, to see stars form and die, to test theories against the universe's own history. The delay gives us depth. It is how we know that the early universe was hotter and smoother, how we learned that heavy elements were forged in stars and scattered by supernovas, and how we dated the first clusters and filaments. The speed limit does not isolate, it organizes. Every change a system makes spreads outward in a growing sphere, marking the region of space that can be influenced next. Physicists call this the light cone. Inside it are events that can be linked by cause and effect. Outside it are events that must wait their turn. Electromagnetic fields, nuclear forces, and the tug of gravity all respect that boundary. The result is a network of influences that keeps the story coherent from atom to galaxy, a web of signals that always arrives in an order all observers can reconcile once motion and gravity are accounted for. Pushing against the barrier still pays off. Particle accelerators add nines after the decimal to the speed of protons and electrons, and, by doing so, reveal new particles and symmetries. Precision clocks flown on satellites and aircraft confirm how time bends with speed and gravity and make navigation possible. Solar sails, high-efficiency electric thrusters, and clever gravity assists can open much more of the solar system to exploration. A probe that reaches a few % of light speed would not break the limit, but it could cross to the outer planets in weeks and the inner Oort cloud in years, turning icy, dim worlds into places we can survey rather than imagine. Gravitational waves enlarge that toolkit. They carry information about masses, spins, and orbits in the last seconds before merger, information that light alone cannot provide. As detectors grow more sensitive, they can time the waves from neutron star pairs and black hole pairs across the sky, tying together how stars live and die with how galaxies build up. If one day we catch a pattern from the very early universe imprinted on the gravitational wave background, it will be because those waves followed the same rule as light and brought us a faithful record rather than an instant summary. The same constant points toward a simple rule for complexity. Computation, biology, and society all require signals to move between parts and return with answers. Those paths take time. As motion through space rises, time for the traveler slows. At light speed, proper time along that path would vanish. A process cannot unfold if its clock does not tick. The limit looks less like a fence around ambition and more like the tempo that allows complicated systems, cells, ecosystems, economies, and minds to exist without slipping into contradiction. Even at the edges of theory, the speed limit remains the reference mark. Arguments about black hole firewalls, which try to keep quantum information safe, take place right at the surface where escape would demand more than light speed. Models in which spacetime emerges from more primitive quantum relations treat C as the fastest stitch allowed in the weave. Thoughts about vacuum decay, a lower energy state sweeping across the cosmos, a sign that sweep the same speed. Whether we look at detectors on Earth, jets from distant galaxies, or the logic of quantum codes, the pulse we find is the same. human projects gain meaning against that backdrop. We are finite beings in a universe with finite limits, but we have measured those limits with astonishing care. We have watched clocks slow at altitude, traced ripples in space-time from colliding remnants of stars, and tuned lasers to cool objects until their motion reaches the quantum ground. The speed of light sits in each of those measurements, not as an inconvenience, but as the anchor that makes them readable. It helps to think of C as a foundation rather than a wall. It secures causality so effects follow causes. It gives time a direction so stories can unfold. It allows stable atoms and long-lived stars, which in turn allow chemistry, planets, and life to develop. It limits travel and communication, but it also grants us a universe we can model, test, and understand. Within that framework, curiosity has room to work, and progress has room to accumulate. The stars do not need us to touch them for their light to teach. Photons leave their surfaces and cross the gulf at the only rate the universe allows, arriving here shaped by gravity, gas, dust, and time. The signal is slow enough to be ordered and fast enough to be useful. It carries the signatures of elements, temperatures, motions, and past events. It builds a map that reaches from the nearby spiral arms to the faint smudge of a galaxy whose first generations of stars are just turning on. The limit is present in every measurement, and yet those measurements add up to a picture that is vast and detailed. Taken together, all of this says the same thing in many languages. Gravitational waves and light keep pace. Hypothetical shortcuts fold under the weight of stability and causality. Horizons in expanding space and in strong gravity define what can be reached and what can be known. Quantum rules protect information without letting messages jump the queue. The largest structures we see grew at a rate set by finite propagation. The smallest ideas about space-time treat the same constant as the fastest allowable update. The boundary that stops us from racing the photons is the same boundary that lets the universe have order, memory, and meaning.